Here's a question for you. Convert the following floating point number to its binary equivalent. Assume 1 bit for the sign, 8 bits for the mantissa, and 7 bits for the exponent. And the exponent, if it's a negative exponent, will be in 2's complement. So here's the number. Let's expand this number out so that we can annotate it a wee bit. So 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0. So this is the floating point number that we're going to be working with. We've got 3 things to do here. Number 1, we need to find the sign of the full number. Number 2, we need to find the exponent. And number 3, we need to find the mantissa. Okay, so let's look at the sign first. The first digit is called the signed bit. And then because it contains a 0, we can say for definite that this number is positive. So the signed bit is 0. Therefore, the number is positive. If the bit had been a 1, then the full number would have been a negative number. Right, next, let's look at the exponent. Now, it says up here in the question that 7 bits for the exponent. So the exponent is always the last set of bits in a floating point number representation like this. The first one is always the signed bit, then follows the mantissa, and lastly comes the exponent. So we need the last 7 bits. So we've got 1, 2, 3, 4, 5, 6, 7. I'm just going to put a demarcation around this so that we know that this is the exponent we're working with. What we need to do is work out whether or not it's a positive or negative exponent and what is the value of the exponent. Have a look at it. The most significant bit is the 1 with the largest value, which is on the most left placeholder. So we can see that it contains a 1, which means this is a negative exponent. So what we can say here is the most significant bit, MSB is an annotation for that. The most significant bit is 1. Therefore, the exponent is negative. So that's really important to you, because now we know that this number has been represented using 2's complement. If that had been 0 in there, then we would know that it was just a regular binary representation of a decimal number, not 2's complement. But in this case, because it's a negative number, we know that it's using 2's complement. So let's work out what the actual decimal value is. So use your tried and tested. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power 7. And write down the decimal equivalents of those places. So we've got 1, 2, 4, 8, 16, 32, 64. Now we don't actually need that one. Let me just get rid of that because we've only got 7 bits here. Right, now what have we got? Let's put in the number. So I'll use orange for that. So it's 1, 1, 1, 1, 1, 0, 0. We can do a calculation on this now. So the most significant bit is a negative number, and it's minus 64 because we've only got 7 bits here. So it's minus 64 plus 32 plus 16 plus 8 plus 4. Now what does that equal? So I'm going to get my tried and trusted calculator for this, And let me just refresh that. So it's 64, and turn that sign to negative, plus 32, plus 16, plus 8, plus 4. And what are we left with? We're left with negative 4. So this is negative 4. Okay, so our exponent is negative 4. So how can we write this down, what we've done so far? It is 0.1100000 times 2 to the power negative 4. Now we need to evaluate it to the answer by evaluating this negative 4. So 0 point, and we're making this smaller. We need to insert our places here. So it's 1, 2, 3, 4, 1, 1. And we don't actually need to put these trailing zeros because they make no difference to the value of this number. So this is the answer. 0110 0000 0111 1100 floating point number can be represented in binary as 0.000011.